Hey physicists, in this little video I'm going to be talking about collisions, both inelastic, those are ones where the two objects stick together, and elastic, where the two objects separate after their collision. Hey, in this little simulation we can represent our momentum by these red and blue rectangles, same as we've done before. The width of the rectangle represents the amount of mass that we have, so I can change the math by just sliding this around. I can change the height of the rectangle, okay, by sliding this slider back and forth. Notice that if I go negative, that the bar drops below the x-axis. I'll leave this at 2 meters per second in the positive direction. Same thing with the red. I can end up sliding this back and forth, changing the width of the red rectangle. In this case, I'll leave it at 300. And then we can change its height by sliding this back and forth. The height of that rectangle, in this case, we're going to make it negative. The height of that rectangle represents the velocity. The area of each of the rectangles indicates the momentum of each object. Hey, in this case, we're looking at both the blue and red carts. They're going to be interacting because we're looking at both objects that are interacting and there are no other external net forces. Our momentum in total before our collision will be the same after our collision. Here we can do a quick calculation. We can see that we have 200 kilograms and 2 meters per second. Our blue rectangle has an area of 400 kilogram meters per second. The red rectangle is 300 kilograms wide, -1 meters per second high. So we have an area or momentum for the red car of -300 kilogram meters per second. When we look at total momentum for both the blue and the red, 400 kilogram meters per second plus the -300 kilogram meters per second tells us that the total momentum here is 100 kilogram meters per second. And after our collision, the total momentum will still need to be 100 kilogram meters per second. Take a look at the bar chart. So over here, what does it tell us? Because they're locking together, both objects have the same velocity. Now our total momentum stayed the same, but we can see that each of the objects had quite a change in their momentum. The blue car had a decrease in its total momentum. The red car had an increase in its total momentum. Those changes were exactly equal. Remember, the impulse that the blue car applies to the red car is the same magnitude but opposite direction that the red applies to the blue car. That's in keeping with Newton's third law. In the upper right-hand area, we can see that there is a graph of force versus time, which is impulse. Okay, so now we're going to look at collisions where instead of the two objects sticking together, they bounce off each other. That's referred to as an elastic collision. Now in an elastic collision, because each of the objects bounce off the others, we'll see a greater change in the momentum. Okay. We'll see a greater force after the collision. But remember, our total momentum to start off with will still be equal to our total momentum after the collision. The only difference will be that the distribution of those momentums. Because they bounce off each other, they will not have the same velocity. We'll go ahead and slide this over. Notice as I slide this over, our previous run gets a little bit dimmer. I'm going to run this a couple times so you can see this. First, concentrate on the forces on the upper right-hand corner. I'm going to run this. Notice our previous run had just under 10 newtons of force. Let's run this again. Okay. You can see we have a much greater force in our collision. Now notice our momentum before is exactly the same as it was in our inelastic run, but notice our momentum after and our change of momentum will be greater this time. I'll run this. Greater changes of momentum because we see that the objects not only stop but they change direction. a different distribution of our momentum afterward. But again, our momentum before was 100 kilogram meters per second. Afterward, it's also 100 kilogram meters per second, but divided differently between the two objects. And we'll run this again. So let's take a look at our key points. If we're looking at both of the objects that are interacting and there are no other net external forces, momentum before, total momentum before, equals total momentum afterward. Each of the objects can have an individual change. When we take a look at these changes, they'll be exactly the same but opposite in direction. Why are they that? Because in this case, the red cart was experiencing a positive force, equal and opposite to the force that the blue cart was experiencing. The change in momentum that the red cart was experiencing was equal to the impulse on the red cart. The change in momentum of the blue cart was equal to the impulse on the blue cart. And because the positive change that the red experienced in momentum is exactly the equal as the negative change in momentum of the blue, there is no change in momentum. Momentum is conserved or the same for the total system, blue and red, as it is after the collision.